Now the last stop in our lecture on EM and Gaussian mixture models is to apply EM to estimate the parameters of Gaussian mixture models. Okay, so at each iteration we're going to keep track of an estimate of the mixture weights, the W's, the cluster centers, which are the mu's, and the covariances, which are the sigmas. So let me show you the notation for that rate, which I have right here. Okay, so at iteration t, we have estimates of each of these three things. So WKT, that's the probability to belong to cluster K. That's our estimate of it at iteration t. Mu are the cluster centers at iteration t, and then sigma are the covariances. So let's do it. E step and then the M step. All right, let's start with the E step. So the E step is to compute the probability that the cluster for I is K. We do it for a generic I and K. Okay, we have to compute this for all I and K. Okay, given the current point and the values of the parameters, which of course the theta is exactly this collection. It's W, it's mu, and it's sigma. Okay, those are the parameters at iteration t. Now we have to compute these probabilities, and we're going to do it using Bayes' rule. Okay, so here it's just going to be Bayes' rule. And so let me write that out. Okay. Now, the two terms in the numerator, I know what they are. I know that this one is going to be WKT, just by because of the assumptions of Gaussian mixture models, right? The assumption is that the popularity of cluster K is WK, right? And so we're going to use what we have at iteration t, which is WKT. And now these probabilities here, according to the Gaussian mixture model, once you know which cluster you're in and you know all the parameters of all the clusters, then the probability that X is what it is given by a normal distribution with mean mu KT and covariance structure sigma KT. What do we do about the denominator? Well, luckily the denominator is, if you expand it in terms of the law of total probability, it's actually a sum over K of terms exactly like the numerator. So we'll just write sum over K of terms like those in the numerator. And then we should be okay. So let's write that out. And that's good, because if it's a sum of terms like those in the numerator, it means we can compute everything in here. Okay, so let's actually just write this out. Okay. Okay, cool. All right, and this is gamma ik, and which iteration is it for? Well, depends how we index things, but I'm going to index it for iteration t plus 1. So we'll say that we're at iteration t and we want to figure out what's going on at iteration t plus 1. So we'll compute the gamma for iteration t plus 1. Cool. So that's actually the E step for iteration t. So I'm just going to put a big box around this, because this is actually the formula we need. One of the two big formulas we need. Okay, so let's go to the next one, which is the M step. Now for the M step, we have to update theta, so we have to update W mu and sigma, all of the W's, mu's, and sigmas, by setting the derivative of the auxiliary function to 0. Okay, so let's, with one constraint, which is that the sum of the mixture weights always has to equal 1. So let me just write down, I'm not going to do all the math for you, but I will at least update what the math actually, I'll at least write down what the math actually is here. Okay. So I'm going to skip steps on updating mu and sigma, and I'll just tell you what the answer is. In fact, you don't really even need the math to know the answers, because the answers they're sort of obvious and they couldn't be any other thing. So let me actually write down the mu and the sigma results as if I had taken the derivative of a and set it equal to 0. Okay, so for the means, as you can see, it's simply the mean of the x's. It's simply the mean of the x's weighted by the probability to be in cluster K. Okay, so this is, it's obvious in the sense that there could really be no other answer, right? Right. The gammas are the probabilities to be in so gamma is the probability to be in cluster K, right? And that's what gamma is. And so this is just the xi's weighted by their probability to be in cluster K. So yeah, there can be no other result, and you really truly didn't need optimization to know that this would be the answer. Okay, so let's write down the covariances, which again, there could be no realistic other answer, otherwise you'd know something was wrong. So let me write down the answer for that one, as if I took the derivative of a, set it equal to 0. So again here, it's just, you can see it's a variance weighted by the probabilities to be in each cluster. So again, you wouldn't have it any other way, right? It's the variance of clusters weighted by the probability of membership. Okay, now we're almost done. We have a little bit more work to do. So right now what we have, the state of what we have here is we have the probability that point I comes from cluster K given all of the parameters, the W, mu, and sigma, which are the gammas. And we have also the cluster, our current estimate for the cluster centers and for the cluster covariances. And the last thing we need is an update for the mixture weights, the sort of general popularity of each cluster. Okay, so that one's a little trickier. I can't just set the derivative of a to 0 because it's actually constrained. We need to make sure that the sum of the mixture weights adds up to 1 so that it's a discrete probability distribution. And for that, we need to write down the Lagrangian and take the derivative of that and set it equal to 0 because we're doing constrained optimization. Okay, so let's start working on that. Okay, so let's write down the Lagrangian. And remember, we're solving, the only variable left are the mixture weights, the W's. Everything else has already been updated. Okay, so let's write down the Lagrangian. And that is my Lagrange multiplier. And it's 1 minus sum over k wk. Okay. So the weights have to add up to 1, and so that's why the constraint is in here like this. Okay, so 1 minus that sum has to equal 0. Now, the only variables that we're interested in are the WKs, and the WKs are right here, and they're also buried in there. Okay, so if I write down the derivative of the Lagrangian with respect to WK, actually, I'm going to write it down with respect to WK prime. I'm just going to take a derivative with respect to one of the W's, WK prime. I'm choosing K prime because there's sums over K everywhere, and so I just want to distinguish my special K that I'm working with from a general K that's in the sum. All right, so let's write that down. Okay, good. So now I can write down the definition of the auxiliary function on the next line. Okay, this probability, we can get it directly from GMM's generative model. It's the probability to be in a specific cluster times the probability to be at the value you are given that you are in that cluster. Okay, so let's just write that down. There we go. And now this guy is going to be WK. That's the quantity we're interested in, but just for K prime, not for all the K, just K prime for this particular derivative. And then this one is a normal distribution, as we know. Okay, so let's just put that all together. Now life gets a lot easier because we're only taking the derivative with respect to WK prime. And so all of the other terms that depend on all the other Ks, they don't depend on K prime. So actually the sum over K gets wiped out and the only term we have to keep is the 1 over K prime. So that makes things a lot easier. And yeah, so let's do that. All right, now it gets even easier because we have log of this times that. And so that's the same as log of the first one plus log of the second one. Well, the second one doesn't depend on WK prime. So actually that term just gets wiped out. All right, so let's simplify. Well, that got a lot simpler. Now, taking the derivative of the log, we're going to get 1 over WK prime. All this stuff just comes straight out. So let's just do that. Okay, now setting this equal to 0, because we're taking the derivative here and setting it equal to 0, the Lagrangian. And what we get when we do that is an expression for wk prime at time t plus 1. Okay, so this thing equals the sum over lambda. Okay, we're not quite done. We're going to use our constraint to figure out what lambda is, because we know that the w's, right, the mixture weights are normalized, so they have to all add up to 1. So let's use that to figure out what lambda is. So lambda is the sum over all of these w's, which are all, it's the sum over all of these terms here. Now if I reverse the sums, and remember that these gammas are actually probabilities, then we'll figure out that the inner sum is actually 1. So let's write down the fact that these are probabilities here. Okay, and there's endpoints, and so there we got it. All right, so lambda is actually n, which means I can go back and edit my expression for wkt plus 1. Let me go and do that. All right, that's the last piece. So we are actually done with Gaussian mixture models and the EM algorithm. So again, just want to go over the 3 steps here. So first, the E step, where we compute these probabilities. The probability that each point is in each each cluster K. Those probabilities are all right there. Then after that, we start with the beginning of the M step, where we have to update the cluster centers and the cluster covariances. And then at the very end, we update the mixture weights, which are down here, right there. And that's it. We just keep doing this over and over again until everything's converged, and hopefully you'll get a good local optimal solution, and you'll be happy with your mixture weights, your cluster centers, and your cluster covariances. That's it.